All right, everybody, let's get into our next topic. Again, building a foundation for preparing for inferential statistics. We covered probability last time, so keep all those things in mind. And now we're going to talk about our next topic called inference. And here's what we're going to cover in this section. We're going to talk about sampling and populations. Remember, these were terms we brought up back in week 1 in the introduction section. And so we're going to cover those again in more detail, and then we're going to wrap up with something called central limit theorem. So let's get into inference and this idea of sampling and population. So let's start with talking about the population. Now I want to remind you, and hopefully this comes back to mind, that the population is the larger group that's being examined, but can't be directly or holistically studied, right? It'd be very hard to do that. So for example, say that you wanted to study the effect of a memory exercise you developed, and you wanted to see if that can help people's memory who are aged between 65 and 85, and you wanted to look at everybody between the age of 65 and 85 in the entire United States. That's millions of people. That's a lot of people, and they really can't be directly studied. Okay, but that would be the population that you're really interested in, that larger group that can't be directly studied. Now, the symbol for the population is a Greek symbol called mu or mu. It looks like a U with the left side going down a little bit further to the bottom. So that represents the population mean. Okay, so keep that symbol in mind. The standard deviation for the population is symbolized as a lowercase sigma. So if you remember, capital sigma is the E looking symbol that means to sum. So the lowercase version of sigma represents the standard deviation for the population. Okay? So the population is too large, I can't study it directly. So what I can do is I can take something called a sample, right? Just like I take a sample from the food at the grocery store, right? I take the little slice of cake that they give me, and then I study, quote unquote, that piece of cake to try and draw a conclusion about the larger cake it was taken from. So I can't study the effect of memory exercises on 65 to 85-year-olds across the whole country, but maybe I can choose a local nursing home somewhere in my neighborhood, and I can go and gather some 65 to 85-year-olds at that local nursing home and study the effect of memory exercises on them, right? Take a small sample and I study them, and then I want to see if I can apply my conclusions of the sample to the population. Now, the symbols for the sample are ones that you've already been introduced to. I just didn't make this distinction between sample and population because I was waiting to get here. So the mean for the sample is represented by X bar in the equations. Outside of the equations, it's represented with a capital M. Standard deviation, lowercase s in the equation, capital SD outside of the equation. So you have mu, and sigma, lowercase sigma for the population, mean and standard deviation. You have X bar and S, or M and SD, for the sample mean and standard deviation. Now, when we're studying samples and populations, what we're primarily interested in is the average score of the population. I want to know, does my memory exercise increase the average memory score of the population that I'm studying, right? Because the average is that one number, remember from descriptive stats, measures central tendency. The average is one number that represents most of the people that are in my data set. So I'm interested in the average score of the population. So when I'm looking at the sample, I'm interested in the sample's average. And what I really want to know is how close is my sample average that I find to the population's average? That's what I'm really interested in. So ideally, you want what you can conclude about your sample average to apply to the population average. What you find out about your sample, you want to what's called generalize to the population. So if I find that my memory exercise increases memory recall for 65 to 85-year-olds by about 20% on average, I want to be able to generalize that to the broader population of 65 to 85-year-olds. I want to be able to say that, yeah, these memory exercises will probably increase memory recall in the population of 65 to 85-year-olds by about 20%, just like with the sample. So that's something that's one of the core logical pieces to samples and populations and inferential statistics is I want to study a small group, find a small average, you can say, and see if I can generalize what I find about that sample and the average to the population and its average. Now, something I want to introduce to you at this point, which is going to come up later when we learn our first inferential statistic and then the ones after as well, is something in the calculation called degrees of freedom. It's essentially a statistic we use in calculating our sample statistics that helps ensure that our sample approximates the population. This calculation varies by test, and so in each test that you learn, in each statistic you learn, it'll be specified how you calculate that. So at this point, just write this down for your notes so you have the concept in mind, and you'll learn more about it as we get further on in the course. So let's really hone in on looking at our samples in our population. So one of the things about our sampling is that we could draw a lot of different samples from the population, right? So I can take sample 1, sample 2, sample 3, sample 4, sample 5, and onward, right? But let's just work with 5 samples in this example. So I have 5 samples driven from population, and I calculate an average for each of those samples. And ideally, you would expect your sample average to reflect whatever the population average is. So if I show you a normal curve, and let's say that our population is normally distributed and its average is in the middle, where would our sample average fall in relation to the population average? Where does our sample average fall? How close or how far from the population average? Let's say the sample 1, ooh, that's pretty close, a little bit below the population average, but super, super close. We wouldn't expect it to be identical because the sample is not identical to the population, right? Slice of cake is not identical to the whole cake, but we expect it to be very, very close, we would hope. Sample 2. Sample 2 is a little further from the population, but still kind of in that center area. Sample 3, about the same distance as sample 2, just a little bit on the left side. Sample 4, almost looks like 2 standard deviations above the population average. So that sample really is not close to the population very much. And then sample 5, wow, that one's in the tails. That one's really far away from the population average. So obviously we want sample 1, but we're not guaranteed to get a sample 1, a sample like sample 1. When we randomly sample from the population, I randomly gather a group of people from the population. Like I randomly choose a local nursing home and gather 65 to 85-year-olds. I hope that they're going to be very close to the population, but I could have gathered a sample that's going to be very, very different from the population. I want sample 1, then I got sample 5, not the one that I really wanted here, okay? Now, why is that important? Why does that matter? Okay, this whole thing here that I just explained is setting up for our next concept called the sampling distribution. Remember that you could theoretically sample infinite amount of times from the population. You could take as many samples from the population as you wanted. And what we could do is we could plot all of our sample means on a distribution, just like I did in that previous slide in the picture I have again shown for you here on the bottom right. So we could plot all of them and see where they fall. We can see what samples fall in the center, closer to the population average, and we can see which ones fall more in the tails, further from the population average. So we can see the distribution of sample means. And ideally, you want to get a sample from the middle because you want to get a sample that's closer to the population mean, not a sample from the tails. You don't want a sample that's from the tails of the distribution that's far from the population mean. So again, another picture I want to show you here that if we have a bunch of sample means and the mean is like, say, 5, I want a sample mean that's close to 5, right? I don't want a sample mean that's 8 or 2 that's further from the population mean. I want one that's closer. And I should have a higher probability of getting one from the center, right? Because the more that it happens, the more likely I am to come across it, right? It's more likely to find something near the average than it is to find it far from the average. More likely to find something in the center rather than the tails. So we hope, we have a greater probability of getting a sample mean from the center than from the tails, but getting one from the tails still could happen. Another visual I want to show you here. Imagine taking your distribution of your sample data, right? Let's say that the one on the left is sample 1 and the one on the green one on the right is sample 2. And so their averages are kind of representing their their distribution of data. And so then we kind of overlap that with the population distribution, the sampling distribution essentially with the population. And we want to see how close the sample mean is to the population mean. And I ideally want my sample to overlap as much as possible with the population. The less they overlap, the more different they are. And I want my sample to be as close to the population as possible, because the closer they are, the better I can generalize, the better I can take my conclusions about the sample and I can apply them to the population. Now, why am I hammering on the sampling distribution so much? It's for three reasons. The sampling distribution and understanding how it works is so important because it helps us understand the population mean, right? The thing about the population is that since I can't directly study the population, I don't actually know what the population mean is. So I'm actually using a sample to kind of give me some insight into what the population might be like, since I can't study the population, it's too big, right? So if I know the sampling distribution, if I know that if I randomly sample from a population, that sample could give me some insight into how the population works, how well the sample mean relates to the population. That's point number two. But the sample could be from the tails of the sampling distribution, which means that it's not going to be very close to what the population looks like. And I need to be aware of that. We need to be aware of that if we're doing inferential statistics, because I need to know if my sample is close or far. Is it similar or different from the population that it was drawn from? Okay. And the sampling distribution is very important for calculating something called the sample error of the sample distribution. It's a number that helps us identify how different our sample is from the population. So let's talk a little bit about sampling error here. Now, the difference between my sample of 65 to 85-year-olds and the overall population of 65 to 85-year-olds, the bigger the difference is between my sample and population of those people, the greater my sampling error is going to be. So what you're looking for is a very small sampling error, right? 0 would be no error at all. You're never going to find 0, because remember, your sample is not identical to the population. The only way you'd have a sampling error of 0 is if you're studying the population itself, and that's not the case, right? We always have a sample, smaller group taken from the larger group. So there's always going to be some amount of error, because the sample is just by nature going to be different from the population. But you want it to be as minimal as possible. You don't want it to be very, very large, because the larger it is, that's showing you that you've got a sample that's more different from the population. In fact, you might have gotten a sample that's in the tails of the sampling distribution rather than the center. You got one where the average is far from the population mean, not close to it. So you want there to be as little sampling error as possible. Now, one of the primary statistic that's used to measure sampling error is called standard error. Now, it's essentially the standard deviation of the difference between the sample and the population. Think of it as you taking the differences between all of the samples you could have drawn and finding how different they were from the population mean, and then you taking the average of all of that. It's just like how a standard deviation works. You take every number and you subtract it from the mean, and then you add up all those, you average all those differences in a sense, and then you get one number that represents how different are all my numbers from the mean. Same thing with the sampling distribution. You take the differences of the sample means from the population mean, and you then kind of average them all together. Now, the standard error isn't actually calculated in the way that I just explained, because we actually don't have the population mean. So it doesn't work around, and it's something that you're going to learn as we go through. Every inferential stat has its own way of calculating standard error that you'll be walked through. The very basic version of it is symbolized with a lowercase s with a subscript x bar. You see that symbol combination there. That is the representation for standard error, which is a measurement of how much sampling error do you have. So you want your sample to be as close to the population as possible. So you're looking for a standard error that is as small as possibly can be. It will probably never ever be 0, but you want it to be as close to 0 as it can be. So here's a question as we begin to wrap up this topic here. How can we ensure that any one sample we draw will be closer to the population mean? Think about this when you're sampling people. You don't have all the time and resources to take 100 samples. Sometimes you only have enough time and resources to take one sample. So you have one sample you can draw, and you want that sample to be like sample 1, close to the population mean. You don't want it to be like sample 5 where it's in the tails. You really want that one sample you take to be from the center. Is there any way that you can ensure, like kind of make it more likely that you're going to take a sample closer to the center versus one that could be in the tails? And the answer to that is you have to increase the sample's size. The larger the sample you get, the closer it's going to be to the population. Because the more people you get, the more people from the population that you're studying, and the more that there is, the more it's going to start to resemble the overall population, right? What's going to be closer to the population? If the population is 1 million people, for example, what's closer to that? 500,000 or 500? A sample of 500,000 is going to be much closer to the population because it is half of the people versus only 500 of the people. Now, still studying 500 people could be great, but studying even more could be even better. So you want a larger sample size. The bigger you can get it, the better. So the bigger the samples, the closer the sample means are to the population. So the larger N leads to the sample mean getting closer to the population mean. Larger N leads to X bar getting closer to mu. That's the thing to remember here, all right? And a little illustration here on this graph on the side here. This is just showing how a sample mean gets closer and closer to the sampling distribution, gets narrower and narrower as your N increases, right? In fact, when say N equals 100, your curve looks practically leptokurtic, which means there's not a lot of variability in your sampling distribution. That's exactly what you want. The narrower your sampling distribution, the more likely you're going to draw a sample that's closer to the population mean, because the curve is so narrow, it's not, the tails are so small, almost non-existent, right? If N is 5 as a comparison, oh, you could draw a sample from the center or from the tails. You have a lot of variety there. The sampling distribution is has a lot of variability. So you want less variability in your sampling distribution, and bigger N's lead to that. Now, the fact that a bigger N leads to the sample mean getting closer to the population mean, this is all called central limit theorem, okay? As N increases to infinity, the sampling distribution approaches normality and then gets even more narrow, just like you've seen here on this graph here. And the more normal it gets, the more narrow it gets, even after normality, the more likely you are to draw a sample that's going to be very close to the population mean. Now, if you click on this link here, it takes you to a fun little web app where you can see this happening with some visual representations of this. You can click on different situations and see how if you increase N, that the curve of the sampling distribution just gets more and more normal and gets even more and more leptokurtic the bigger that you make it. Really fun to play with to kind of illustrate this point of central limit theorem. I want to show you one more thing to illustrate this pattern here. I want to show you these 3 histograms that we have, okay? And on these histograms, this is representing data that comes from a sample of varying sample size. So the one at the very top, this is data with a sample size from a sample size of 10. The middle one has a sample size of 25, and the last one has a sample size of 50. Now look at how the curves of the data, look at the shape of this histograms, how they get more and more normal, right? The bars are more and more following the shape of a normal distribution. Most of the data in the center, few in the tails, the bigger your sample gets. That's what you want. A bigger sample will look more and more normally distributed like that. And you can also see the standard errors. Take a look at the standard errors here. When N is 10, your standard error is 0.37. When it goes to 25, it gets smaller, it's 0.2. And then when it's at 50, it gets 0.14. Those look like small changes, but those are actually pretty significant drops, statistically speaking, in regards to standard error. So the bigger your sample size, the smaller your error is. And the smaller your sampling error is, the closer your sample mean is to the population mean. And then finally, to wrap it all together, the closer your sample mean is to your population mean, the better you can generalize what you find out about the sample to the population that it was drawn from.